Richard Artoul is the CEO and co-founder of a company called WarpStream. WarpStream is taking an innovative, and I think we might say aggressive approach to building a cloud-native Kafka. They've made some decisions about trade-offs that they're willing to make in order to get the operational simplicity that comes from radical cloud nativeness. And it was really fun to dive into the architecture, kind of see how it works. Let's listen in to me and Richard right now. Hello and welcome to another episode of the Real-Time Analytics Podcast. I am your host, Tim Berglund, and I'm joined today by Richard Artoul. Richard is the founder and CEO of a company called WarpStream, which is based on some really exciting ideas, and glad to have him on the show. Richard, welcome.
Thanks for having me, Tim. Excited to be here.
You got it. Tell us what WarpStream is, and if you want to back up and tell us how you got there, your call. What's WarpStream, and how did it come to be?
Yeah, WarpStream is the way I like to explain it is it's a drop-in replacement for Apache Kafka. So it's compatible down kind of the wire protocol level from your application's perspective. It looks exactly the same, but that's basically the only thing that it shares with Kafka. Like, it's a complete kind of clean room reimplementation of the system. And the thing that's kind of interesting about WarpStream is you kind of think about it as like, what if, Kafka had been built, this year, basically, for the cloud, instead of, 13 years ago for data centers. And so the two big things, I guess there's kind of like three big things about WarpStream. One is the data plane is basically completely stateless. So instead of having like brokers with disks that store all the data on local volumes and partition leaders and all that kind of stuff, we just have basically a bunch of thick proxies that are completely stateless that we call agents that store all the data in object storage. So that's like one big part of it. The other big part of it is just how it kind of reduces costs by using cheap storage and eliminating interzone networking. And then the third kind of big difference between it and like Apache Kafka is we have this like really big data plane control plane split. So you can kind of deploy the data plane into one environment or one VPC or one cloud account, and the control plane can run somewhere else completely. And so that's kind of how our company basically provides, something that looks like a managed service, but keeps all the data in your cloud account.
There you go. That bring your own cloud approach is increasingly popular. The big twist here being the approach to state. And it might be good a little bit to dig into that, what I'm calling bring your own cloud approach to things. But let's dig into the data plane. You said agents, which are thick proxies. And so my layperson's understanding of WarpStream, which I'm coming into this conversation with, is it's like Kafka, except all the data is in S3. Now, I know we say S3 and, we mean cloud blob store of your choice, but take that. And by the way, dear listener, if that sentence leveled you up on WarpStream and you're just coming to that level of understanding now, cool. That's kind of where I am. So take me from there and flesh that out or correct it, or what's the deal?
That's pretty much an accurate statement. There's like basically there's kind of like the thing I like the kind of obvious contrast is between like, okay, the contrast I think between WarpStream and a traditional Kafka cluster is like relatively clear. Is like, so you have a traditional Kafka cluster, they each have, so like you think about like, you write some data from a producer client to a Kafka cluster, right? So in Kafka, the way that works is every partition is quote unquote owned by a specific leader broker. That broker is essentially responsible for receiving all the writes for that broker and then sequencing the data, right? So determining the final order of the data.
Yes.
And then obviously putting data on one node with one disk is not, either highly available or strongly durable. So it gets copied to two other brokers who are kind of the followers for that partition.
Yeah. And those followers are responsible in like open source Apache Kafka for pulling from the
correct
leader.
Yeah. And they store like a copy of all the data for that specific topic partition, also usually on local disks. And so in WarpStream, what we do, sorry, go ahead.
Tightly coupled there. So the key point about the way Kafka works is not that there's a lot of compute going on in the broker. It's intentionally minimalist, but what compute there is to kind of babysit the connection, receive things, decide what's available for reading and all that kind of stuff. That's all tightly coupled to the storage. It's right there on the other side of a PCIe channel from the processor, as I like to say.
Yeah, exactly. And it's
Yeah.
also like, for example, let's say you you have a traditional Kafka cluster. You're like, I want to write to topic foo at partition 3. There is exactly one node in the cluster that can receive that write at any given moment in time.
Yep.
Even if you have a
Yes.
cluster with hundreds and hundreds of nodes, one person has to receive it, and there are two other very specific nodes that can handle the replication for that data. Um, and if one of those nodes goes away, you have to go through a leader election, and if a follower disappears, when you replace it with a new node, they have to like copy back in all the data that the other node previously had. So very stateful, basically,
Right.
with Kafka. And so with WarpStream, it's kind of the inverse of that, which is all of the data is stored in S3. All of the replication is handled by object storage. All of the durability is handled by object storage. And so it happens in WarpStream actually when your client first connects to a WarpStream cluster. The first thing that a Kafka client does is like, hey, I care about this topic. Tell me who the leaders are for all the topic partitions so I know where to send batches of data to. And so if you have let's say a 50 node Kafka cluster, you'll get back, 50 nodes, and it'll be like, this one is the leader for these partitions, that one's the leader for those partitions. When you connect to WarpStream for the first time, what WarpStream actually does is it tells that client that one of the agents is the leader for all of the partitions in the cluster. And the way we do that is we just essentially pick, it's not random, we use kind of like a global round robin load balancer. And the reason we can do that is because WarpStream agents, because they're basically completely stateless, any agent can handle writes or reads for any topic partition at any time. So they really are basically completely stateless, and none of them are special. And if you delete one and like replace it with a new fresh container, there's no like bootstrap sequence. It's kind of like the same way that like you kill Nginx and then you just turn it back on. There's no like a bunch of state that needs to be reconfigured or whatever.
Right.
It's very similar to that.
Okay. I mean, it does need to know things about the world, but where does that state live? Does it? It seems like it would need to know the topic and partition metadata at least.
Yeah. So the way that stuff happens is it's handled via um, our control plane, or sometimes I call it a metadata store, depending on what you're thinking
Yeah.
of. You can kind of think of it as like our metadata store is kind of like if you had a single like kraft replication group, basically for the
There you
entire
go.
cluster. And so so going through the full sequence again, like a client connects to an agent, it starts producing some data. It could be for hundreds of partitions in one produce request. It all gets sent to the single agent. That agent kind of buffers that data in memory for a short period of time, and then flushes one file to object storage that contains data from all of the topic partitions from all of the clients that it received produce requests from during that time period. So it creates exactly one file in object storage, which is another big difference with Apache Kafka. Kafka has these files per topic partition. When you switch the object storage world, that becomes very expensive. So we have to make multi-topic
Right.
partition files. And then once it does that, once it's created that file in object storage, it then goes to the control plane and says, hey, I just created this file. It contains batches of data from these 30 topic partitions. What are the offsets? And then the control plane essentially acts as a metadata sequencer for the whole cluster. And so the control plane's like, okay, that batch for this partition, it's offset 60. This one's 937. So all of that kind of stuff that normally happens in a specific broker to do the ordering, which is kind of implicit in Apache Kafka, is handled in our control plane. And then only once those two things are done does the produce request get acknowledged back to the Kafka client. And so the thing we call this is like, so kind of traditional data lakes, you have this concept of like a separation compute and storage. It's kind of like the more cloud native way of doing things. We kind of describe this as going like one step further, where we have separation of like data and metadata, which means that like if you look at an object, if you look at a file, like when we write data to a file in object storage, we don't actually have to know the order of the batches yet. We can just flush the data, and then the data gets ordered independently by the control plane. And what kind of pops out the other side is the full semantics of Kafka. You have topics, you have partitions, you have ordering within a partition. It's just the way we get there is different, if that makes sense.
Yeah. And so on read, then the control plane is going to provide the metadata necessary to
Correct.
provide the ordering semantics that you expect.
Exactly.
Yeah. Okay.
So a consumer will come in and be like, I want to read for this partition. What files do I read in which order? And the control plane will be like, oh, you need to read them in like this specific order. And if you read them in that specific order, you get the correct ordering of the records out, basically.
Got it. And in your example, you said that batch produce request could have had 200 partitions in it and all kinds of things. Formally true, and then that's in that one file. But my guess is, in the typical case, you don't have that. People produce to a topic, and so there are going to be however many partitions in that topic, or maybe just one partition, because that's how a lot of producers are going to work a lot of the time. And so you get this nice efficient. This file just has these messages from this partition in this topic. Does it work out that way often, or am I? Is my view of Kafka writes a little
it depends
utopian
on how people are using Kafka. Like obviously for us, and actually for traditional Kafka too, it's way better. So that there's this concept of like different partitioners in Kafka, and so like the default one is called I think it's called like the default sticky partitioner. And so if you don't assign a key to every record, like what the Kafka client will do is like it'll write a bunch of data for one partition, then move to the next partition, then move to the next partition, and so you get these really nice sized blocks of batches of data for each partition, and the number of total partitions that you're writing to in a small amount of time is low. But the kind of worst, I don't want to say worst case scenario, but the most difficult workload to handle, really for all Kafka implementations, is one where you have a producer writing to a topic with a high number of partitions, and it's essentially writing, essentially round robin, one record at a time across all the partitions. So you can imagine a client producing to a topic with 1,000 partitions, which is not that uncommon, especially kind of like higher volume stuff. And it generates a produce request that has one record and per partition. So you have 1,000 batches, each with one record. That is expensive in basically all Kafka implementations, but it is a thing that people do, and that we have to basically design for and load test. So it really is workload dependent. But yeah.
Okay. Is there any kind of background process of consolidating or merging files? Does it get messy in the blob store and you want to clean things up?
Yeah, if we just let that run forever, eventually what you'd end up with is like tons and tons of files.
Yeah.
And everyone kind of is, not everyone, but there's this idea of the kind of like the small file problem where reading, historical data becomes expensive because you have to make a bunch of IOs against a bunch of tiny files, and with object storage, it's really expensive. And so there's two ways that we have to solve that. We have to solve that for like the kind of live consumers, and then we also have to solve that for historical replays.
Right.
And we solve it, and the reason we solve it like twice basically is that the background consolidation process won't kick in fast enough to deal with essentially what the live consumers have to deal with. Because you can imagine, if you have 3 agents, maybe it's not a big deal. Each consumer is talking to like 3 files. But when you have hundreds of consumers and you have 50 or 100 agents, the number of files and number of partitions, the number of IOs that you would need to power the live edge would be really huge, right? Because it's not like all the data for one partition is ending up in one file. It's ending up kind of scattered across all the files for all the agents.
Right.
Sorry, it's kind of hard to do with my hands, but
and if you're listening to just the audio, like Richard and I are gesticulating,
and so for the live consumers, what we do is we have this thing called like we call it the kind of like distributed file cache, but what you can think about it is like a really smart IO scheduler in the agents, and what it essentially allows us to do is basically, even if you have tons of consumers that are reading tons of partitions and issuing very tiny reads and IOs, that gets translated into very large batch reads from object storage, which are then chunked up and cached in memory, and then all the little reads are served directly out of that in-memory cache. And the reason that works is that basically, if you think about how Kafka workload usually works, you have a bunch of consumers and they're kind of like caught up, right? They're reading the live edge. And so everyone's doing that at the same time. And then what happens is, eventually someone they falls behind, or they want to go and read a bunch of his data in the past. And that's where the background consolidation process you were talking about kicks in. We call that compaction basically. And the really kind of naive explanation is we take little files and we make big files.
And of course you don't want to make them too big, because then there are other costs, but there's LSM tree energy.
It is an LSM, right? Basically. It's very much an LSM.
Okay,
yeah.
There you go.
Yeah.
Not off base. Good. Okay. And it's also funny that you mentioned Nginx, because those agents are in the storage or the data tier. They kind of smell like reverse proxies, like they're sort of Kafka aware reverse proxies.
Yeah, that's exactly what they are, basically.
There. And the metadata lives in the control plane and somewhere. That's in the managed service, but some more conventional database or something like that, right?
Yeah, kind of. It's actually fairly custom, just because the thing that happens when you, like, we couldn't just like use Zookeeper and throw it all in there or whatever, because the amount of metadata that this architecture generates is like huge. And so it's a very custom implementation, but it is all basically built on top of cloud primitives as well. Like our cloud control plane doesn't have any local disks either. It's all built on top of cloud primitives, because for basically the same reasons, to make our lives easier, to make it cost effective, and to make it so we could provide a really mature and robust cloud service without spending years and years programming against raw disks, basically.
Right. Obvious question. I'm sure you get this. Yeah, but isn't that slow? So this sounds like a legitimate latency trade-off, but how much of a latency trade-off is it?
Yeah, it is totally a legitimate latency trade-off. We've put a lot of work into making that basically as close to the like theoretically minimum possible you can get, based on like the profile of performance of object storage in cloud environments. And so what you'll see in for produce requests is about a P99 latency of about 400 milliseconds. So like your Kafka client sends a produce request to the agent and it gets an acknowledgement back. You're looking at about 400 milliseconds at the P99. And then end to end, like from your producer sent a batch of data and your consumer managed to pull it out of WarpStream and read it, end to end, P99 there will be about just under 1.5 seconds. Is kind of what you're talking about. So it is kind of, there's definitely a latency trade-off there, but we still consider it very much like real time. It's really only if you have essentially like, there's some kind of narrow subset of use cases where that latency is too high, but for the mass majority of use cases, it works out okay.
Yeah. Oh, and that's the name of the game with latency trade-offs is you're offering something that maximizes some other utility in exchange for this. Yeah, sure. Some of the time, you can't make that trade-off. You have to have everything in memory or whatever, you know, or just conventional Kafka because you need that dial to be in a different place. You get you said without spending years programming against raw disks, and so there's an obvious operational simplicity to this. I mean, I'm intrigued because there's kind of an elegance in the radical cloud nativeness of it.
Yeah.
Lots of people say cloud native, and I feel like you're saying, no, wait, and hold my beer.
Yeah. It's an aggressive architecture for sure. Yeah.
This is cloud native.
Yeah.
And that's why I'm fascinated by it. I think that's a really cool approach. And I suspect we'll be seeing more of this in data infrastructure. Now, like from a StarTree or an Apache Pinot perspective, again, that's the thing where by default, storage compute tightly coupled, you're looking at latencies where nothing else in the world will do, and you need that. And, forget everything. I need a 50 millisecond P99. Everybody get out of my way. And so, you're going to spend the money on that. That's what you need. And there are those use cases where you need that. But even at like StarTree Cloud, we have a tiered storage thing where we did some smart stuff with object stores. And if you can afford a few hundred milliseconds for the older data, you save money. So what am I getting? Because it's a cloud service. So in a sense, me writing code against producer or consumer, I don't care about your operational simplicity. That's your job. So what on the user end, what am I getting? Is it a lower cost, a little lower total cost? What's the trade-off for me?
Yeah, this is a really actually good question. And there's a number of aspects to it. The first I would say is like, you say you don't care about operational simplicity because it's like a managed service and all that type of stuff. But actually, I think a lot less people. How do I say this? I think a lot more people wish they could keep a lot more infrastructure in their own environment than they could.
Mm-hmm.
And the reason that they do move everything to cloud environments is because it's so annoying to operate themselves. that they're just like, I'll pay someone to do it, and I'll just like send all my data out, and I don't really have much of a choice. The fact that we've made it operationally extremely simple means that our BYOC model looks a little bit different than other people's, which is that like we don't have to punch in. You don't have to give us IAM permissions, and we punch in and deploy a Kubernetes cluster, and we deploy like 9 services into your environment and that type of stuff. Our BYOC model looks like, here's a container, single container, and here's a Helm chart, or you can put it in ECS. Really put it in your environment however you like to put containers in your environment. Auto scale it on CPU, and then never look at it again. And so we don't have any access to your cloud account. None of your data leaves your cloud account, and it can just fit into like whatever weird network topology you have. However, some other team configured things. We don't have any opinions on any of that. And so it actually enables, I think, like an entirely new kind of flexible deployment model that looks it's not all BYOC is the same, I guess I would say. So I think that's part of the reason.
Good point.
That the operational simplicity really matters to people. That's one part of it. The second part I would say is it's like radically more cost effective if you can make the latency trade-off. Interzone networking, like if you're doing high volume stuff, you're sending logs, you're sending IoT data, any kind of machine generated telemetry, probably a lot of the stuff that people end up putting into, Pinot as well. Anything like that, a lot of the money you're spending on Kafka is just for interzone replication. And nothing fixes that except eliminating kind of the disk entirely. Even tiered storage doesn't really address that problem completely. And so you get radically reduced cost there. And then obviously, cloud disks are super expensive. Like people don't realize how much expensive it's like, a GP2 EBS volume is 10 cents per gigabyte. Triply replicated is 30 cents per gigabyte. Unless you're going to run your Kafka broker at 98% disk utilization, you're going to end up paying 60 cents per gigabyte to keep it at like 50% capacity. So 60 cents per gigabyte for EBS volumes versus 2 cents per gigabyte for S3. That makes a huge difference in costs. And then the third thing, which is people I don't do a good enough job of explaining normally, but like imagine you like. So here's a really cool thing, for example, you can do with WarpStream that's interesting. A lot of times people will be like, hey, I have this Kafka cluster. My producers are over here, but I have consumers in a completely different VPC, a different cloud account, a completely different region, right? And I want to be able to read the data too. And then, you have to go get a PhD in cloud networking to figure out how to do like VPC peering across cloud accounts, across regions, or use private link and do all this kind of stuff. With WarpStream, what you do is you just go deploy more agents in that other place. And then you make sure they can both talk to the same S3 bucket, which is like a trivial thing to do in all clouds. And you now have a multi-VPC, multi-cloud account, multi-region Kafka cluster that just works. Like you can produce over here and you can consume over here, and you don't have to know anything about cloud networking to make that work.
And those agents just need to be able to talk to the control plane.
The control plane and the S3 bucket, correct.
Of course, S3 bucket.
Yeah.
Okay.
And then another thing that's kind of interesting, just one more thing, is another thing that comes up a lot is people are like, hey, I really need to something happened and I need to replay all the data for this topic. And let's say you have a big cluster, 30 or 40 Kafka brokers, but the partitions for that topic are just on 3 nodes, basically. And so it doesn't matter how many Kafka brokers you have. You want to read all that data. The limit is what those 3 brokers can do for you. Without disrupting the live traffic on those 3 brokers. With WarpStream, if you want to read 10% of the topics in your cluster, but you want to spread that load across 50 or 100 agents, you can literally in 2 minutes add 50 more containers, then just spin up a ton of clients, and the load will go through all of the agents instead of just 3 of them, because you don't have to read specific data from specific nodes. So it ends up looking a lot more like you get a lot of the benefits that people traditionally associate with a data lake in terms of massive concurrency and scalability, but you get the semantics of Kafka. Yeah.
And the load balancing is baked into the Helm chart for the agents?
It's all handled kind of transparently via the control plane. So the control plane essentially acts as the kind of zookeeper or KRAF for the cluster, and it does that kind of
That'll help the clients get an answer that is a load balanced answer.
Yes, exactly.
To where they need to talk. Okay. A little history briefly. How'd you come by this idea? I mean, it's one of those things that, again, it's not a solution. It's a trade-off. Everything is a trade-off. It's a super compelling one. And as soon as you describe it, it's like, well, it's so obvious, but nothing is obvious before somebody comes up with it. So where'd the idea come from?
Yeah, there was a couple of things I think that had to happen. One is like I said, it's like in a really aggressive trade-off that was like not clear if was going to be a good one before we started. I think now it's kind of clear, but beforehand it wasn't. But it happened. It was actually all my co-founder Ryan's idea. Actually, I think it was like more than 4 years ago. He pitched me, we should either build a logging database built on top of object storage, or we should build Kafka on top of object storage. And I was like, Kafka on object storage, who cares? Kafka's so boring. Let's build the logging thing. Because I had just I hadn't had a ton of experience with Kafka at that time.
Sure, it is sort of a some men would just want to watch the world burn kind of answer, but there it is.
Yeah, and there are times where it's definitely, I have a couple of gray hairs from this project for sure. And so we ended up building the logging system. It's it's powers basically all of the products except metrics at Datadog. It's called Husky, and you can think of it as like Husky is to ClickHouse or Elasticsearch what WarpStream is to Kafka. So we built this kind of object storage first, completely stateless, schemaless observability data lake at Datadog. And we learned a lot, I think, about the like performance envelope of using object storage as the only system, and like exactly kind of all there's a bunch of little tricks that you have to like add up one at a time, and without any of those tricks, like WarpStream doesn't work. It's too expensive, it's too slow, you can't implement the Kafka semantics. And I think after several years of building another system that was completely designed around object storage, the shape of WarpStream kind of started to make a lot more sense. And it's a little bit of a different problem. Like, it's kind of understood now how to build a data lake on top of object storage, right? You like make a bunch of files concurrently, you have an external metadata store, you add compaction, you add caching to taste or whatever. And because you don't have this kind of strict ordering guarantee, um, it's just a more well understood problem. How to get the semantics of Kafka without any disks, basically, to buffer on, was not, I think, is not as well understood. And it kind of, it took us a long time to kind of work out all the details.
If folks want to learn more, where do they go?
Our website's great. So you can just go to warpstream.com. There's links to our Discord and Slack community channel. You can book a call with us. Our engineering blog's also really good. Less gesticulating with my hands and more proper diagrams to learn from. You can find everything from our website.
My guest today has been Richard Artoul. Richard, thanks for being a part of the Real-Time Analytics podcast.
Thanks for having me.
And there you have it. If you feel compelled to help us spread the word and grow the real-time analytics community, you can give us a rating on Spotify or Apple Podcasts or wherever fine podcasts are sold. If you're watching us on YouTube, hey, subscribe and, of course, hit that notification bell. And you can always share your favorite episodes on LinkedIn or Twitter or wherever it is you do social media. Thanks, and I look forward to talking to you in the next episode.